Hello and welcome to this next session on infrared spectroscopy, where we will be discussing the applications of FTIR spectroscopy. So we'll be looking at not only quantitative, but maybe also some qualitative methods of use of infrared spectroscopy and discussing some other sort of use cases, such as in kinetic studies and things like that. So, the majority of use cases of infrared spectroscopy are really based on the kind of qualitative measurements. So species determination. So looking at which species are present in our solution or in our sample. So using FTIR for analysis. So FTIR or IR is used for qualitative analysis, which is its best use. So the qualitative analysis here, we can identify functional groups in the group frequency regions, and we can compare with standard spectra containing these functional groups, such as in the fingerprint region. Sometimes people dismiss the fingerprint region as being hard to interpret. It's easier to interpret than you might think. And saying that kind of throws away a huge part of the spectrum and sort of just says, well, I'm not going to use this, but actually you can use it for further determination of the presence of certain bond types. Then for quantitative analysis, we have the use of concentrations in solution and things like that. However, IR is more difficult to use than UV-Vis because of the narrow bands, which is due to the variation in the energy. We have a more complex spectra. We have weak incident beams, low transducer sensitivity, and as well as that, there's the problem of solvent absorption into the, if we're using, like, for example, a salt window, that we can't use, for example, water as our solvent. We need to use non-polar solvents, and generally we don't want to be using solvents at all with regards to our infrared spectrometer. Usually quantitative analysis is not the way we go about this, although it is possible, but usually we want to use UV-Vis for that because of the broad bands, the easy identification of the peak position and things like that. Disadvantages for quantitative IR measurements are the spectral complexity. So there's a lot of peaks present, the frequent non-adherence to the Beer-Lambert law. So it's not always going to be linear with regards to concentration. We have the narrow path length cells are inconvenient and contribute to analytical errors. So oftentimes the concentration of our samples in the FTIR is much higher than what we would use for the UV-Vis, which kind of causes it to not adhere to the Beer-Lambert law. However, it also causes problems where when you have a longer path length, you have a more reliable statistical average of your sample, whereas the narrow path lengths, usually in the region of microns for FTIR measurements, we end up with analytical errors because the short path length means that we're not necessarily guaranteed a perfect representation of our sample. So we have a bunch of characteristic peaks here. We have different spectral regions. So we have from in the sort of like the low regions around about 400 to about 1,000. We have things like CF bonds, CCl bonds. We have ethers, this COC bond structure. We have organometallics, so carbons bonded to metals and things like that. 1500 to 1800 is our C double bond O, which we have also encountered. Usually this is a pretty strong peak here, pretty easily identified. Carbon double bond carbon, usually it's like a doublet of peaks. Carbon double bond nitrogen is usually also a pretty strong peak. Then in this 2100 to 2300, we have these nitrogen containing and carbon triple bonds, nitrogen containing species, nitriles here. These are characteristic peaks, which are very easy to identify. They're usually pretty sharp, pretty strong, and well isolated from other peaks. Then from 2800 to 3200, we have the CH peaks, so carbon hydrogen peaks. So these are also useful for identifying hydrocarbons in our system. And then from 3200 to 4000, we have our XH, our heteroatoms, where we have our NH, we have our OH, and we have our CONH. So these, especially the OH peaks, we saw before with at the very beginning of this, I introduced you to some water spectra in the gas phase and also in the bulk, and how those could be very broad if they're in the bulk, but we saw well-resolved peaks whenever we used gas phase water. Now the XH heteroatom there is the OH bond in water, and so it's very, very visible and easy to kind of determine. So here are some of our standard frequencies and whether or not they're strong, medium, or kind of variable. So usually it's a good idea to know a few characteristic peaks. You know that carbonyls are around about 1600, 1700, something like that. We usually have OH stretches from 3500 and above. Some are lower, but generally what we have is 3500 and above, which their broadness can vary. It varies with regards to like how many hydrogen bonds are being formed. So if there's a lot of hydrogen bonding, typically creates a broader spectrum. Then we have our things like our alkenes, our nitriles, which are very strong. Our nitrile region here is like around 2200, 2300. It's a very narrow range, usually a very, very strong peak. And it's a very good marker of the presence of a C triple bond N. Our C double bond O we've talked about before, usually in this like 1700 region. So these are important peaks to remember, like amine peaks as well. And some alcohols. It's often a good idea to go online and search for spectroscopic problem sets where people have created model spectra or obtained spectra of relatively simple compounds, and then they have asked you to try and identify them just using a table of data, table of common peaks. So usually, for example, if this was a problem in a quiz or an exam or something, there wouldn't be that many of them, probably just one per exam. And you'd be given a table of common frequencies to use, and then be asked to try and assign the molecule based on your knowledge. So IR spectroscopy using gas samples. So gases fill this gas well, the gases fill the gas cell. So here is Pike Technologies gas cell. So what we have here is like two little tubes where we can, so this is set up for two reasons. So what we can have is we can have an entrance point and an exit point. So over here, we can see an entrance point and an exit point. So this is if we want to do a flow through. So for example, say we were doing a reaction and we wanted to monitor it as it was going on. And this is possible with FTIR because of how fast it kind of passes through. So what we see is the sample entrance and then exit. So for example, say we were reacting some sort of hydrocarbon, an unsaturated hydrocarbon with hydrogen gas over a platinum metal, we can try and just measure this. For example, we could measure the hydrocarbon, and then as we start to introduce hydrogen gas into the reaction vessel, we can pass through our products through here, and they will flow from the sample out, or from the sample entrance through the sample exit, and then we can measure that as a function of time, or we can just put a gas sample in here and measure. That's probably the easier way to do it. So we have transparent windows here and here. They're not transparent to our eye, but they're transparent to infrared radiation. So we have here sodium chloride and potassium bromide. Those are the typical windows. So they're just like two little discs of these. The thing is, though, if you're going to use these, we all know that sodium chloride dissolves well in water, and these kinds of salt dissolve well in water. So potassium bromide also dissolves really well in water. So it's going to create a problem where if the room is too humid, we're going to get degradation of this window, and we're going to end up destroying our nice sample holder. And these are not cheap. To get a really, really pure sodium chloride transparent window is relatively expensive. So as a result, we need to be very careful with our measurement conditions. And generally, inside of our spectrometer, we also have these sodium chloride windows. So our spectrometer needs to be kept in a temperature and humidity controlled environment. It needs to be very dry, not too dry, but very low humidity. And often these FTIR spectrometers have very well dehumidified casings, which need to be like there's a cartridge of silicon beads, which needs to be replaced regularly in order to maintain a super dry environment inside so that the transparent windows don't get destroyed by atmospheric water. Now, of course, a little bit of water is not a big deal. Like a little bit of humidity is not going to like destroy it, but like humidities of like more than 50% is very, very dangerous. And typically they have a long path length, typically around about 10 centimeters. And that's because if we remember the gas phase, we have isolated molecules which do not interact well with each other, which means that in the beam path, which is very narrow, we don't actually have that many molecules. And so we need to increase the length of this to give us a higher statistical chance of having molecules in the beam. Liquid samples also possible. The problem with liquid samples is we need a very, very narrow path length because there are a lot of molecules in the path because liquids obviously associate with each other. And so we need to make sure that the path length is very small. So this is something that we might see here where we have two windows and we put the liquid sample in one side and it comes out the other side so that we can measure our sample. This is a very, 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 very small path length, less than 1 millimeter usually, on the order of microns. We can also do it this way where we sandwich it between two discs and then put these two discs. So there's a drop of our liquid sample, put this on top of this and then sandwich them together. Here are some solvents which we can use depending on the wavelength that we want. So these are all solvents which can be used with these sort of sodium chloride windows because they do not dissolve the sodium chloride. And again, of course, that means our liquid sample should also not interact with salts. So there's a lot of things to consider here whenever you're doing FTIR spectroscopy of this type, which is ultimately why a new technique was developed called ATR, which we will see shortly, which kind of improves the chances and makes everything a little bit easier to do. So FTIR practical considerations. So unlike UV vis, many solvents absorb in the IR. So the cell path lengths are much shorter and higher sample concentrations are needed. Solid samples can be measured in a KBR matrix. So what we're doing is we're dissolving some of our solid into a KBR and then making a pellet, which is then measured in our FTIR spectrometer. So instead of using a KBR window and sandwiching our material between that, we're just like basically mixing it with KBR. Now KBR does have a peak, but it's usually pretty different from our sample, and it comes from the absorbed water on the KBR. So we have here this 1 to 100 weight to weight ratio. We usually use high pressure to form the pellet, and then the water bands, that's just to compress everything so that what we're getting is not just air. And then the water bands present at 3,450 and 1,640 wave numbers, but none of this comes from KBR. It's just the water absorbed on the KBR. We can also disperse it in mineral oil, which is called a mole. So we can either use KBR matrix or a mineral oil mole. Again, this is just the solvents which are going to be transparent in most FTIR wavelengths. So here is at the bottom is a little look at that sample holder that we saw a moment ago for our liquid samples. We have a back plate, we have a front plate, we have neoprene gaskets, which can like just create a nice seal there. Then we have a window, which is transparent to our FTIR, then our infrared frequencies. Then we have a spacer, which the sample goes inside of. Then we have another window which sandwiches the sample holder, the neoprene gasket, which then allows a good seal and everything to be compressed together nicely. And then we have these nuts for that are easily tightened and released. So the process here of doing IR spectroscopy using solid samples is to make a semi-transparent pellet with KBR. It's semi-transparent because there are those absorbed water peaks. And then we grind and mix with a Nujol mole to form, a Nujol to form a mole. And then we put 1 drop between sodium chloride plates. And the spectra of the NuGel must be subtracted to get the proper spectrum of the sample. Okay, so a little bit of, I guess, the molecules. So this is an FTIR spectrum of a certain type of molecule. Here at the bottom are some characteristic, what do you call this? Characteristic peaks, which may be useful for you to try and identify the molecule. Just kind of give it a go. See if you can even just identify a single bond that might be present or not. And just try it. Pause the video for more time, and we'll have a little go. Like I'll give you an example. For example, in this region here, there aren't really any peaks. This is probably just noise. I would not classify these as peaks, especially considering knowing that these peaks are all very strong from our table earlier, and me talking about the fact that like things like nitriles had strong peaks, and these alkynes also had strong peaks. So in this region here, we would expect to see a very strong peak, probably similar to some of these peaks, if the structural moiety was present. So for example, if we had a nitrile bond, a C triple bond N, we would expect to see a very strong peak here. We do not. So there's probably not going to be a C triple bond N or any of these others present in this spectrum. So yeah, again, pause the video for, I'll give you a few seconds, pause if you need more time, and then we'll just a little bit of fun, see if you can guess the molecule. Most of the information down below should give you a good starting point. Okay, so there's, again, pause if you need more time. So let's have a look at it. So there's clearly a peak in this region. The ones that are highlighted here are those which are really the strongest in this region. So we don't really have a presence of any heteroatoms. It would be hard to say if there's going to be a nitrogen or a hydrogen there. There may well be an OH bond. There is definitely something here. There's possibly an OH bond. It looks like we definitely have some CH bonds. Like that seems to be definitely something that's present. And here as well, this is a less well-known CH region. Then over here, we have this strong peak here. It could be any one of these. I'm going to say it's probably, if we have a presence of an OH bond, we may well have an alcohol. So I'm going to say it's probably a C double bond O. So let's see what we got. All right. So we have, in fact, acetic acid. So there's two hydrogens. There's a methyl group here, and then there's this carboxylic acid group here. So we have the OH stretch, which we talked about before. We have the CH stretches here and here. And then we have the strong peak here. So this is a very characteristic peak of a C double bond O. And so we have the presence of that. And so that indicates to us that we probably have an acid. So that's just like a kind of little exercise to try and test your mind and see if you can use some of the knowledge that we've gained. So the applications of FTIR, so all organic and inorganic molecules absorb IR, thus we can use it to determine a huge number of species. So for example, the analysis of hydrocarbon mixtures. So if we have these different spectra, like we can see that they have different peak positions, like here is orthoxylene, methazylene, paraxylene. We have ethylbenzene, we have the cyclohexane solvent. So the cyclohexane solvent goes like this. See, that forms the background, so it doesn't absorb here. So again, because this is molecular absorption spectroscopy, it follows this Beer-Lambert summation rule, where the total absorption at a particular wavelength is going to be equal to the sum of all of the individual absorptions. We can also use it to determine air contaminants, things like sulfur dioxide or nitrogen monoxide. Those all have characteristic peaks which can be measured, and they can be identified as being present in the air or not. So as I mentioned earlier, attenuated total reflection, this ATR method, is really useful. What it does is it effectively analyzes only a very small portion of our sample, which is directly directly placed on top of a window. This window is usually a diamond crystal or some sort of zinc crystal to measure our infrared spectroscopy. Now, the samples here directly measured are either solids or liquids. We cannot measure gases with this, although gases are not really a difficult sample to measure anyway, so long as we have that long path cell that we saw before. So gases can be measured pretty straightforwardly. So ATR is attenuated total reflection infrared spectroscopy. We'll see on the next slide exactly how that works. And so samples can be examined directly in a solid or liquid state. No preparation is required. We simply place the sample on top. If it's a solid sample, what you can do is you can use this press to push it against the crystal a little bit. It's not always necessary, but it can give a better fit. If it's a liquid, the liquid will adhere to the crystal pretty easily. No preparation is required. It is used to analyze coatings and opaque liquids. It requires high refractive index material, as the refractive index of the crystal must be greater than the refractive index of the sample. So usually the crystals that we use are going to be diamond. So ATR, attenuated total reflectance. So this is how it works. So this is the schematic of a multiple reflection ATR system. So we have our IR beam incident through the crystal, and it passes through the crystal. Now, what happens is that above the window, is the sample, which is in contact with the evanescent wave. So basically, the evanescent wave is kind of like overflow wave that will come in contact with the sample and is what we will use to measure. So a beam of IR passes through the ATR crystal, which is either diamond or zinc selenide, which is then covered by the sample, which is either solid or liquid over the top here. The incident infrared light reflects internally, forming an evanescent wave. So this is the path of the light. You can see it kind of over, and it creates this evanescent wave effect where like the wave kind of overlaps into the sample where the sample would be. So the wave extends into the sample by a few microns, which is why it's really useful for measuring liquid and solid samples, because usually our problem with those kind of samples is the saturation. So there's too much sample and it just totally destroys our absorption spectrum. But with this technique, we can get exactly as much as we need. So it's a very small amount. So when the beam exits the crystal, it is collected by a detector and analyzed and displayed, similar to a typical IR spectrum. Diffuse reflectance spectroscopy drifts. So it drifts diffuse reflective infrared Fourier transform spectroscopy is useful for the examination of powdered samples, and so it also has minimal sample preparation. We just simply mix it with KBR, and so hard polymers can be analyzed, and this is qualitative, not quantitative. We cannot use this for quantitative measurements because we are mixing it with KBR. So the IR beam here is seen to be interacting with the sample in a diffuse reflective reflectance experiment. So the IR beam is incident on the sample, and then it is going to be reflected in many different directions. Okay, and then finally, we talked about near IR before. So this is analysis is similar to mid IR, but the range is much higher, beyond 4,000 wave numbers, from 13,000 to 4,000 wave numbers. It's previously not really used that much, but it's gained a lot of use because you can get these sort of like handheld measurement devices, which will allow us to actually, its major use is in customs. So they can analyze goods which are incoming to the country and make sure that there's no like things which shouldn't be there. So it is measured in, it's used to measure protein, moisture, starch, oils, lipids, and cellulose in oil seeds and grains. So this is in reflectance mode like this. So this is reflectance mode setup. So what we can do is we can measure the quality of grain very quickly, and that can help to classify it, and therefore make sure that we have like class A, class B, class C, and so on, different oils. And so those can be properly sold at market. Determination of water content in organic films and glycerol and things like that can be used to check film thickness, and even in the analysis of narcotics with PCA analysis. So those are some of the applications of infrared spectroscopy. Thank you for watching.